Alright, this video is the first section of chapter 3.1, Extrema on an interval. So we're going to go up through three parts before we do examples to go through some of the background knowledge. So first, extrema of a function. Alright, extrema are points at which the value of a function is either largest, we call that a maximum, or smallest, we call that a minimum. So anytime throughout this video, you can pause to write down some of the definitions. But this is what we're going to be talking about throughout the whole video, both maximum. So, first example, identify the maximum and minimum values of the functions represented in the figures over each interval. So I'm going to call this figure 1. This will be figure 2. And this will be figure 3. Now, let's take a look. So in figure 1, we want to identify the maximum value and the minimum value. The first thing that I noticed is we have a closed interval. All right, our interval is closed right here, and we're also continuous over this interval. So when I look here, first for the maximum, I'm going to look at my largest value. For maximum and minimum values, you state what the y value is. So I see right here, this is my maximum. All right, and I see that point is 2 comma 1 2 3 4 5 2 5. So our maximum is 5. You choose the y value. Now for the minimum, I need to look at my graph. All right, I see that the minimum value occurs right here. All right, at this point right here, it's that vertex of what looks like part of a parabola. All right, and our minimum value is 1. Now let's look over at figure 2. So figure 2 is a little different. Here I have an open interval. I see that my function is not defined at the endpoints. Now, for this open interval, I want to identify the maximum, and I want to identify the minimum. All right. When I try to identify the maximum, this point is not defined. I can't actually find the maximum for this function on this open interval. So I'm going to say there's no maximum. All right, it's not defined at that maximum. All right, and then for the minimum, I still see this point right here. We do have a minimum. It's still 1. All right, still 1. All right. Next, let's look at figure 3. All right, we need to identify the maximum. So I see this function is defined at its endpoints. All right. So our maximum is going to be, we have 2, 5, so our maximum is 5. But then we have a discontinuity at our minimum. So when I look right here and I try and identify the minimum value of the function, there's no minimum. All right. All right, let's keep going. Now, the extreme value theorem has to do with this idea. If f is continuous on a closed interval ab, then f has both a maximum and minimum on the interval. So the big idea here is go ahead and underline continuous. So for the extreme value theorem to apply, a function has to be continuous. Underline, highlight, box that. This will be on the AP exam. All right. Now, if a function is continuous on a, also you need to circle, box, do whatever you have to do here, closed interval, AB, then f has both a maximum and minimum on the interval. This is called the extreme value theorem. Now, your visual that goes with the extreme value theorem is figure 1. So let's look over here at figure 1. All right, now the function is continuous. I see there are no discontinuities. All right, it's continuous. All right, and it's on a, and we have a closed interval, meaning our endpoints are defined. Closed interval. So we have both of these criteria for our extreme value theorem, and then we were able to identify a maximum and a minimum. So it's continuous, no discontinuities. We have a closed interval, our endpoints are defined. So we had both a maximum and a minimum. So one more time, extreme value theorem. If a function is continuous on a closed interval, then f, that function, has both a maximum and a minimum on the interval. All right. Now, we can also talk about something called relative extrema and critical numbers. So over here, I have the graph of f of x equals x cubed minus 3x squared. This graph has a relative maximum at 0, 0, so that's this point right here, and a relative minimum at the point 2, negative 4. Whenever you're looking at graphs, you can think about relative maxima occurring at like the top of a hill. So like we got like the top of a hill, the peak of a mountain or top of a hill, and relative minima occurring at like the bottom of a valley. So right here we're going to call this a relative maximum, and down here we have a relative minimum. All right. So again, relative maxima occur at like the exact top of a hill, and relative minima occur at the bottom of a valley. So I even wrote that down for you. Think of relative maxima as occurring at the peak of a mountain on a graph, and relative minima occur at the valleys of the graph. So whenever you're looking at a graph, you can kind of apply these concepts. Now, our official definition of relative extrema, so that whenever we're talking about extrema, you should be thinking about maxima and minima. That's all the way back at the beginning. So extrema are maxima and minima. Let f be the function whose second derivative exists on an open interval I. If there is so again, from here on out, and with some of the AP questions, you have to read this criteria in the AP question, like when it tells you this. So we have the second derivative exists. That's going to be important eventually. So let f be the function whose second derivative exists on the open interval I. 1. If there's an open interval containing c on which f of c is a maximum, then f of c is a relative maximum. If there's an open interval containing c on which f of c is a minimum, then f of c is called a relative minimum. So all this is saying is that if you find a certain function value, all right, that's a maximum. So either that would mean that it's like at the top of a hill on your graph, you call it a relative max. All right, this is saying if you find a certain function value that's occurring at the bottom of a valley, that's a minimum, and we call that a relative minimum. Now, this is the big idea for this video. At each relative extrema, so at each relative maximum or minimum, the derivative is either 0 or it does not exist. All right, one or the other. At a relative extremum, the derivative is either 0 or does not exist. The x values at these special points are called critical numbers. For the rest of our unit, you're going to be working with critical numbers. The key thing you have to remember for critical numbers is either the derivative is 0 or the derivative doesn't exist, like we said over here. Anytime you see or hear critical numbers, all right. So here's our definition of critical numbers. Let f be defined at c. If f prime of c is 0 or f is not differentiable at c, then c is a critical number of f. So critical numbers can be two things. Either the derivative is 0 or f is not differentiable at that value of c. So here's your visual. All right, right here. F prime of c doesn't exist because it's a cusp. So right here, this is where we're looking. The derivative doesn't exist at this point. So this x value right here is a critical number. X values are critical numbers. Say that to yourself like 5 times. The x values at these points are critical numbers. All right. So if the derivative doesn't exist, the x value there is your critical number. All right. Now, the other case is when the derivative equals 0. So right here at c, my slope goes from being positive right here, and then at this point it changes to negative. So right at this point, right here, the slope is 0. Our derivative, the slope, is 0. All right. This is also a horizontal tangent line. So critical numbers occur at places where the slope is 0. All right. So, or wherever we have horizontal tangent lines. So critical numbers occur where the slope is 0, wherever we have horizontal tangent lines. Relative extrema occur only at critical numbers. All right. Now, here are the steps that we're going to be using for some of the examples. So, some guidelines for finding absolute extrema on a closed interval. All right. These are your guidelines or steps. To find extrema on a closed interval, or to find extrema of a continuous function on a closed interval AB. Step 1, find the critical numbers of f. So right here for this step, on step 1, make yourself a note that for step 1 you're going to use derivatives. Alright, after that you're going to evaluate the original function f at each critical number. Then, because it's a closed interval, we also have to check the endpoints. The least of these values is the absolute minimum. The greatest is going to be the absolute maximum. The actual maximum, and then just make yourself a note, the actual maximum or minimum value is the y value. So we're looking for what are my final y values. Where the max or min occurs is the x value, or those are our critical values. All right, so first example. Find the absolute extrema of f of x equals 3x to the fourth minus 4x cubed on the interval -1, 2. All right, so what we can do is run through the guidelines. The step 1 is find the critical numbers. All right, so step 1. All right. All right, now we said that for critical numbers, this is either where there's two possibilities. Either where the derivative is 0 or where the derivative doesn't exist. So what I'm going to do is take the derivative, so I got f of x equals 3x to the fourth minus 4x cubed, so that gives me 12x cubed minus 12x squared. To actually find the critical numbers, you set the derivative equal to 0. Let's factor out a 12x squared. Then I got x minus 1. So now my critical numbers are either x equals 0 or x equals 1. All right. Now, I notice here for the derivative f prime of x, I don't have anything in the denominator, like the derivative always exists. So now, for step 2, all right, so we're going to evaluate original function at endpoints. And critical values. All right, so what I'm doing right now is putting steps 2 and 3 together. We're going to evaluate our original function f at the critical numbers and each endpoint. So what I'm going to suggest doing is just making a chart. All right, so my endpoints of this interval are -1 and 2. So I'm going to put -1 and 2. The critical numbers I found in step 1 are 0 and 1. So we have -1 and 2 are the endpoints, 0 and 1 are the critical numbers. Now, I have to evaluate in my original function, which was 3x to the 4th minus 4x cubed. So let's go ahead and do that. So f of -1 is going to be 3 times -1 to the 4th minus 4 times -1 cubed. That gives us 3 plus 4 or 7. Let's find f of 0. We have 3 times 0 to the 4th minus 4 times 0 to the 3rd. We get 0. Let's do f of 1. That gives me 3 minus 4 or -1. Then I'll do f of 2. So that's going to give me 16 times 3 is 48 minus 8 times 4, 32. I get 16. So now, to review, so far I have, for step 1, found the critical numbers using the derivative. Step 2, I evaluated the original function f at the critical numbers and the endpoints. Now I'm on step 4. The least of these values is the absolute minimum. The greatest is the absolute maximum. So let's go ahead and look. The least is the absolute minimum. So I see the least value is -1. The greatest is the absolute maximum. All right. Now, it can kind of help to sketch out the graph. I'm going to actually plot these points for x and f of x. So I'm going to plot out -1, 7, 0, 0, 1, -1, and 2, 16. So we actually answered the question already. The absolute minimum occurs at 1, -1. The absolute maximum occurs at 2, 16. But let's just get a visual for this. All right, we're going to graph it. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All right, so I got -1, +7. 1, 2, 3, 4, 5, 6, 7. 0, 0, 1, -1, and then 2, 16. So we can just kind of sketch a quick graph. All right, so I can see the absolute maximum occurs at 216, and the absolute minimum for this function on this closed interval occurs at 1, -1. So we can kind of just finish it off. So the maximum occurs at, the absolute minimum occurs at 1, -1. The absolute minimum, or absolute maximum, occurs at 2, 16. All right, let's run through one more example with this concept. All right, find the extrema of f of x equals 2x minus 3 times x to the 2/3 power. All right, on the interval -1, 3. All right, let's run through the steps again. Step 1, find critical values. All right, so the critical values, you should always think derivative. Take the derivative, take the derivative, take the derivative. So let's find our derivative, f prime of x. The derivative of 2x is 2. The derivative of -3x to the 2/3 becomes, you multiply the 2/3 times the -3 and you get -2. You subtract 1 from the 2/3, you get -1/3. And that becomes 2 minus 2 over x to the 1/3. All right, now we have two things to consider. We have to consider, so it's a critical value. Critical values mean two things. Either the derivative is 0 or the derivative doesn't exist. So let's start off by finding when the derivative is 0. So I'm going to have 2 minus 2 over x to the 1/3 equals 0. Let's subtract 2 from both sides. I'm going to have -2 over x to the 1/3 equals -2. Let's multiply both sides by x to the 1/3. So I have -2 equals -2x to the 1/3. Divide both sides by -2. Alright, then to undo the 1/3 power, I can raise both sides to the 3rd power. So I have 1 equals x. So x equals 1. So that takes care of one of our critical values. Now, this is where we have to use some of our prior knowledge. So I found where the derivative equals 0. That's x equals 1. Now, I also have to consider where the derivative doesn't exist. Now, the derivative doesn't exist at x equals 0, because if you look up here, if you plugged in 0 to the derivative, because if you found f prime of 0 is undefined. So I know that f prime of x is what we just found. If I try and plug in 0, I'm going to have 2 minus 2 over 0 to the 1/3. That's not allowed. You can't have 0 in the denominator. That is undefined. So x equals 0 is also a critical number. This is that other case where the derivative doesn't exist. So whenever you're finding critical values, after you have your derivative, make sure to check denominator. Make yourself a note. After taking derivative, check denominator. All right, now we're on step 2. We got to test our critical values. So let's just make a quick chart. So I'm going to have x and f of x. So my endpoints are -1 and 3. My critical values are 0 and 1. I know that f of x equals 2x minus 3x to the 2/3 power. So let's start plugging stuff in. We'll have f of -1. It's going to be 2 times -1 minus 3 times -1 to the 2/3 power. I'm just going to kind of evaluate that on the side so you know what I'm doing. So when I take -1 to the 2/3 power, this is just a side note. This means that I'm taking the third root, because that's what's in the denominator, of -1 squared. But -1 squared, I just changed the notation. Alright, so then you get the third root of 1, which is just 1. So this becomes 2 minus 3, so I get -1. Or -2 minus 3, sorry. -2 minus 3, you get -5. It's my mistake. Alright, now let's find f of 0. That's 2 times 0 minus 3 times 0 to the 2/3. You just get 0. F of 1 gives you us 2 times 1 minus 3 times 1 to the 2/3. We can do the exact same thing down here. 1 to the 2/3 is equal to the cube root of 1 squared, which is 1. So I get 2 minus 3, or -1. Let's find the last one, f of 3. That's 2 times 3 minus 3 times 3 to the 2/3. Alright, let's work it out down here. 3 to the 2/3 is equal to the cube root of 3 squared, which is the cube root of 9. We can't simplify that, so this just becomes 6 minus 3 cube root of 9. Cube root of 9. So the 3 stayed right there. Alright, so then from there, and then if you simplify that, you get approximately -0.24. Alright, so now we can kind of go through and look for our maximum and minimum values. So I see now that the minimum value has to occur right here because that's the smallest number. So the minimum occurs at -1, -5, and the max occurs at, I said to look for the biggest value, 0, 0. Let's add an absolute in front of it. Go ahead and circle it because this is the answer to our question. Now let's just kind of go ahead and graph it just so that you have a visual of what's going on here. So I'm just going to graph these points I found for x and f of x. I'm going to have -1, -5, 0, 0, 1, -1, and 3, -0.24. So if I graph these points that I found, alright, so I got -1, -5, 0, 0, 1, -1, 3, -0.24. Now when I graph, I'm going to have this. Alright, and I can see right here I had a cusp at that 0, 0. So if we hadn't identified 0 as being a critical number, we wouldn't have had this correct. Alright, so this concludes the Introductory lesson on extrema on a closed interval.